Hello guys, welcome to the channel EC TechNest. Today in day 20 of the 100 days digital design and Verilog series, today we are going to speak about ring counter and Johnson counter. Both these counters are synchronous type of counters. That means all these flip-flop will have a common clock signal. One main thing to notice is a ring counter is a circular shift register where the output of the last flip-flop is directly fed as an input to the first flip-flop. Here you can see Q3 is being fed as an input to the input of the first flip-flop. Here we have one more line other than the clock, that is overriding input. We'll discuss in detail about this in the next slide. Just to tell what is it, this is a preset signal for the first flip-flop and all the other three flip-flop will have clear signal. Then we have the structure. It will have n flip-flops connected in series depending on the number of bits that you are using. The Q output of the last stage of the flip-flop will be given as input to the first stage. Here it requires a manual preset. Typically you set the first flip-flop to 1. That means preset is 1 and all the other flip-flops will have 0. The one hot effect. Only a single logic 1 circulates through the ring. Here what we mean to tell is when it works as a shift register, what happens is the first preset that you have set as 1 will keep on shifting. We'll discuss this using the truth table. It will be easy for you to understand. It has exactly n states for n flip-flops. A 4-bit ring counter has only 4 states. Ring counter, how the ORI signal works. That means overriding input signal. The first thing is it is connected to the asynchronous inputs of the flip-flops. That means it has preset and clear. First, we'll learn about what is this preset. The ORI line is connected to the preset pin of the first flip-flop. When the ORI signal is activated, it forces Q0 to become 1, regardless of the clock. It doesn't bother what is going on in the clock. And the other three, what you're seeing clear, it will be set to 0. Now there is one issue. It is called a self-starting issue. You might have thought, why do we require this overriding input? This is where it comes into picture. The flip-flop would power in a random state like 0000 or 1101 randomly. So to avoid this pattern, and it will not self-start. So we require this specific pattern 1000 to begin circulating. The ORI line, the overriding input line, 1 minute, yeah, bypasses the clock. This is crucial because you want to initialize the counter before the first clock pulse arrives. It means whatever preset clear your value you are giving, that has to be given before the first clock pulse arrives. See, this is what I was talking about. Your preset stage is 1000 and the 1 gets shifted. 1 it is getting shifted to the next flip flop. That is how it completes the counter from 1000 to again 1000. Now this is how we write the Verilog code. We have two inputs, that is clock and your overriding input signal. Then you have an output register, that is 4-bit Q, because you're using a 4-bit ring counter. Always the positive edge of the clock and positive edge of the ORI, that is overriding input. So one thing you have to note this: if ORI is 1, that means if your overriding input is 1, you will give the Q to be 4-B1000. That means you will give an that means you're just setting the previous state. Here, whatever you had the flip flop, right? Here it will have 1000. You are just giving a preset value to it. Else begin. What you will do here is, this is, you need to understand this carefully. What I'm trying to do is, whatever value it is there in the last state Q3, I want to give it back as an input. So here I'm setting it as Q0. You'll understand it here. So this is my current, whatever preset value I'm giving 1000, that is this. So what happens is, here the last bit is 0. I've taken it. 3 is to 1 becomes 1 is to 000. Now it is a new queue. That means whatever I'm writing the code here, this is a new queue. This is your old queue, this is your new queue. New queue means updated one. So what it will become? Your Q0 value is 0 and 3 is to 1 will come here. So it becomes 0100. So the shift has occurred. So this is how you will do the whole ring counter. Now, very simple. Here we have a Johnson counter. It is also called as a twisted ring counter or switch tail counter. This is because here it has a very minimal change. One thing you have to understand is there we gave a normal output of the last flip flop as input to D naught. Here we are giving the inverted output or complemented output. Then circuit and working. It is very similar to the ring counter. What happens is there you use the last normal complement without the complement to the input. Here you are using the complemented form as an input. Usually you begin with all zeros. No special one hot preset is needed. There you have to give one what is that 1000 as preset. Here it is not needed. Again, we'll understand this using truth table. The creeping effect. There you had the one hot effect. It fills the register with ones one by one and clears them with zeros one by one. There, what happened was here it had only four states. Within four states, the whole counter got completed. But here it is not like that. It has 2 power n states. That means it will have 8 states. Let us see. You are beginning with 000. So your last output is Q3. The complement of that will be given as input, right? So you will get 1 as input output here. 1000. So again it will become 1. So we'll come until fourth pulse where all will become 1. And again this will repeat, right? 1 will again get complemented, so become 0 1 1 1. Again this one gets complemented, become 0 0 1 1. In a similar way, all the 8 pulse will get completed. This is happening only because here we are giving Q3 bar, that is the complement form of Q3 as input to the first flip flop. Then use case. Ring counter is generally used in stepper motor controller digital clock where you need to activate one line at a time. Johnson counter is used as a frequency divider. It divides the clock by 2n or to generate multiplace square waves. Let us see the Verilog code for this. Not much has changed. Here I have just written the ORI signal as reset. It is okay. You can write it as 0. Because what happens is there we are not mentioning any preset, right? We are not giving value as 1000. Here everything is being given 0 itself. See, it starts at 0, right? So it can be called a reset itself. At positive edge of the clock or positive edge reset, we begin. If reset is 1, your Q output will be all 0. This is your older Q. Now, if you want to update the newer Q, a similar concept, what we discussed, how the Q is getting updated. Only thing that is changing here is you are using a NOT because you have the Q bar as input to the first flip flop, right? And else it remains the same as this itself. Whatever value we discussed here, in a similar way, it will happen. Thank you. If you have any doubts, feel free to put it down in the comment section.